Greetings. My name is David Hauk. I'm the Vice President of Embedded Safety Critical here at Parasolt. It is my pleasure today to introduce Gurunath Ramaswamy from Qualcomm, who is the Director of Engineering at Qualcomm Automotive. I've had the pleasure of working with Guru for over 3 years now, and I can tell you that Guru brings both vast experience and focused passion for the topic today. He is a key to Qualcomm's success in accelerating the digital transformation in automotive software. More personally, he's an outstanding guy to work with. Parasolt is proud to have Guru and Qualcomm as a customer, and the opportunity to support them facing the challenges presented in the sometimes turbulent world of automotive software testing. In today's session, Guru will provide an overview of Qualcomm Automotive, talk about what they're building and testing for compliance, how they have addressed the challenges along the way. Ladies and gentlemen, Guru Ramaswamy.
Hey everyone, thanks Josh and thanks Dave for the nice introduction. Okay, so today's presentation will focus on what Qualcomm did to achieve functional safety software compliance for its system on chip software, the SEooC software that we have. And I will give a quick introduction to Qualcomm, especially on the ADAS solutions that we have. We call it the Snapdragon Ride solution. And after a quick introduction to the overall solution, we will go deeper into the functional safety concepts. I will start with the functional safety concept, and the focus would be mostly on the software side. So we would pretty much go into every section of ISO 26262 Part 6 on what Qualcomm did to achieve the safety compliance and what are the challenges we faced along the way. Also, we will focus on how Qualcomm and Parasolt work together. That's one of the main focus in this meeting, and how we had a tool selection criteria and how Parasolt fit the bill well and how our interaction happened. So feel free to stop me anytime for any questions. Given that we have only 30 minutes, I kept things at a very high level because this could easily be a 2 or 3 hour presentation. So I just put a single slide which has the key points. And if you want to go any deeper into any of these slides, you can stop me and ask questions, or if you want to also contact me offline, you have all the details here, and I believe Josh will send those details later. Okay, so let me get started. So Qualcomm has the main ADAS solution it has is called the Snapdragon Ride platform. You might have seen in the press, we already have multiple customers and multiple wins recently with the Snapdragon Ride platform. But basically, this is how it looks. At the very bottom, we have the scalable SOCs. We have multiple SOCs which would cater to different ADAS levels, the SAE levels for all the way from L1 to L4. And we have a complete software stack on top. The first 2 things you see in the stack is what Qualcomm provides. We have a operating system environment and what we call as the Ride SDK, which has middleware tools and libraries. After that, we work with various partners, or sometimes the OEMs take care of it themselves, to have a complete driving stack. Recently, we have partnered with Arriver. We acquired Arriver to implement some of the driving stack, the drive policy and the front-end surround vision thing. And we also have partnered with few others to provide a complete driving stack. Any questions on this?
No questions at the moment, no. Feel free to keep going. I'll mention it if any come in, Guru.
Okay, sounds good. Okay. Now going a little bit deeper, little bit into detail into the, so I'm trying to move around slides a bit here. Okay. So now we will, take a look at the hardware we have at the bottom here, the Snapdragon Ride SoCs. going a little bit into detail into an SOC, you can see that we have a pretty complex system on chip. We have various, I'm sorry, wait, I'm not sure why it keeps moving. Okay. Just give me a second. I'll keep it like this for a moment. We have various subsystems within the SOC. We have a hexagon neural processor, which does the neural network processing. We have separate what we call IP cores, or smaller pieces of hardware within the SOC for display, safety, security, video processing, camera processing, GPU, and the CPU. So one of the challenges is, for achieving safety compliance in both hardware and software is the SOC is not a simple ECU like thing. We have various hardware, various CPUs within them, various operating systems, etc. Now, getting into the software part of it, we have an auto imaging system, which is basically supporting cameras. We have the camera processing, and then we have a whole neural network processing toolkit so that any neural network can be compiled and executed with accelerated hardware. We also have embedded vision and autonomous driving libraries, and a whole suite of middleware and SOC infrastructure, which is has the operating system and all the drivers for the various hardware, etc. On top of that, we provide development platform and tools for our customers to be able to use our SDK. And along with the ADAS solution that we are supplementing it with other things, support for sensors, support for maps, and then some very interesting new technologies for car to cloud and vehicle to vehicle communication. So with this, we believe Qualcomm has one of the most comprehensive ADAS development systems, and more importantly, a very flexible ADAS development system based on the need of the customer and their stack, etc. It can be implemented in any scalable way that they want. Okay. So this is a quick introduction to the Snapdragon Ride solution. And I also wanted to quickly show where the Snapdragon Ride SoC fits into the overall scheme of things. To keep it very simple, what we have is we have a set of sensors, which the input of which comes into what we call the processing element. And the processing element produces an output, which is sent to the actuators, which control the vehicle. And from the functional safety point of view, we primarily look at 3 to 4 things. So we have what is called a safe input. So whenever any input comes to Snapdragon SoC, be it camera, radar, LiDAR, etc., the hardware and the software ensures that the input is correct and it has the required data integrity. So you have a safe input interface modules. As an example, if there is a camera sensor connected, we check for various things before we process it, whether the frame is not frozen, frame is not corrupted, etc. And then we also have a safe processing. Once we have a safe input, we have various hardware accelerators for neural networks, computer vision, etc. And we do all that processing with ASIL compliance. And then once we do that, we also have a safe output module to communicate to the external VCUs. This is typically done via Ethernet or sometimes PCIe. And we also have ensure safety in any communication that we send outside to the VCU. On top of that, we also have a safety monitoring and health management system. Most of the OEMs typically have an external MCU with which we interact to ensure that there is a monitoring of the SoC. This is typically like clock voltage monitoring, temperature monitoring, and a few other health monitoring, etc. So this is how the Snapdragon SoC fits into an overall ADAS system. Okay, now that we have an overall idea of the Snapdragon Ride hardware and software, let us go a little bit into detail into the functional safety part of it. So both our hardware and our software is developed as a SEooC, a safety element out of context. So typically for a single version of the hardware, we have multiple software products based on different operating systems and different customers, etc. And all of them are developed as a SEooC. Primarily developed to meet ASIL B, to be more specific, ASIL B of D safety goals. And on the software side, we call this the Snapdragon platform BSP software. It's also developed as a software SEooC, which will, of course, work only on the Snapdragon SoC hardware. So this is a pretty, interesting challenge. We have multiple software components developed for ASIL B or ASIL D components. So we have around 50 components, and we have around 5 operating systems, all on different processors, and they all need to talk to each other, but they also not need to talk to higher level applications. And to meet this goal, we work with various teams within Qualcomm to achieve this, but also, based on need, we pre-integrate various third-party software. So I hope this gives you a scale of the complexity that we have to deal with. Pretty much every software component, is different from any other, software component that we work on. And they all need to coexist, meeting the ISO 26262 requirements for freedom from interference and all the ASIL B compliance goals that we need. So in the next few slides, we will quickly go through the various parts of ISO 26262 and some of the challenges and interesting problems. This is just, I think you're all aware of this. This is a quick snapshot from ISO 26262 2018, focusing on Part 6, software development. So it has all these various clauses, starting from requirements to design implementation and various testing and verification. I will just refer to these numbers in the slide so that you get the context of what I'm talking about. Okay. So the first thing we do is when we started the product, the Qualcomm Automotive solution was based on certain pre-existing software elements we didn't have to develop from scratch. Some of you might be aware that Qualcomm has a rich history in various other sectors, primarily the mobile world, the 5G, and we also have other products. So we didn't have to really start from scratch, but we have to leverage on a product which has nothing to do with automotive or functional safety. So one of the first things we did is we did what's called an impact analysis. We looked at all the existing software and figured out how to make it ASIL compliant. We call it safety software binning. Without going into too many details, we use one of the 3 methods. One is we do something called qualification of software components. So based on a certain criteria, and the criteria is primarily these components have been used for a long time and they don't directly impact safety critical modules, so they're not developed just for the safety critical modules. A few examples are the standard libc libraries, which are part of our compiler, and we also have certain security related software which is not directly used in safety, but they're used for certain switches between secure to the non-secure one. And so for these components, we use what is called software qualification. This is part of Part 8, Clause 12 in ISO 26262. This is generally one of the simpler ways to achieve ASIL compliance, where you would follow one of the 4 steps required. I won't go too much into detail, but it's more like black box testing, and you would achieve ASIL compliance on this. And the second idea we use is ASIL decomposition. So here, you have a set of what we call QM components, quality managed component, and we check, can we keep that component as is at QM, but provide safety mechanisms around it. So typically a ASIL B requirement would be split as ASIL B of B and ASIL QM of B. So this works well for certain mechanisms, typically interprocessor, or interchip communication, like Ethernet PCI or certain remote procedure calls that we have. This way, we don't have to go and make the original software we had ASIL compliant, but provide certain safety mechanisms around it to ensure that we meet all the safety needs. So this is, we set, some of our software components fall into this bill. And the third one, if none of this is possible, is we follow the complete ISO 26262 Part 6, where we go through all the implementation requirements, design requirements, safety analysis, everything, which is the most complex one and takes a lot of resources. Okay. So the first thing we realized when we started this process is we looked at all the teams and also some third-party software, and we found that everybody has a different process, different tools, and different coding guidelines to design guidelines. So everything was different. And we had this major challenge to put it all together in a comprehensive way to create a safety case that would satisfy our safety assessor as well as our customers. So some of the key ideas we used here is tailoring. So we had, this is, by the way, part of ISO 26262 Part 2, Clause 6, which allows for project-specific tailoring as well as component-specific tailoring. So for every software component, we have an overall process for the whole Qualcomm Automotive software system, but then we work with each of the teams and have a separate tailoring done for each of these components so that we can still meet ASIL compliance without changing the way they work a lot. The key here we found is that detailed documentation of the tailoring. When we went through the assessment, and we'll talk about that a little bit more, the assessors were fine with using different processes, but as long as it's clearly documented and proven that it will meet the ISO 26262 process for safety. So that is the first thing we did. We looked at all of them, had a gap analysis, and did tailoring for every single component separately. The second challenge is different tools. Everybody had different tools, starting from different compilers and different tools for code review to different tools for static analysis, code coverage, everything. So we tried to have most of the teams follow a certain tool, which in this case is mostly Parasolt. But for few teams which couldn't, then we have to have a separate report which you would integrate. And all the tools used by these various teams, we have around 50 to 60 tools. We have to go through a detailed tool qualification, which is ISO 26262 Part 8, Clause 11. So we first do the tool classification to see what TCL level they fall in. And then we have a Qualcomm defined tool qualification process with the help of our quality team, and we finally produce a detailed qualification report. So one key thing we noticed is this has to be done really very early in the project, because during tool qualification, sometimes we found that some of the tools were challenging to qualify and they didn't have the required processes or the test plan, etc. And we have to switch tools so that we can actually qualify the tools. Similarly, when we are looking for external tools, we always check if they have ASIL certification, and some cases they didn't, and we have to buy our own a test suite, etc., so that we can qualify those tools ourselves. But this tool qualification and integration of tools by various teams is a very important part that we found when we have to work with multiple teams. And the other important part is, especially with our customers, more than the assessors, is like they wanted to make sure the customer requirements are traced to our internal requirements, and then those requirements are traced to the test plans as well as all the implementation metrics like static analysis, violations, code coverage, goals, etc. And in the safety case, we have to present this to our safety assessor. So even though the teams use different tools, different processes, as long as we can prove the traceability, every requirement has a test plan and every component has all these metrics and provided in a single traceability matrix, that went a long way in getting through the safety assessment. Okay. So yeah, I think I wanted to kind of quickly, before going into all the technical details, talk about some practical challenges that we face working with various teams. Okay, so the first step in, once we had the initial environment set up, like we talked in the previous slides, worked with all the teams, set up the tailoring, and looked at all the tools, set up the tools, everybody is good. The next step was deriving the software safety requirements for a complex SOC. So we used a tool internally called JAMA for the requirements management. What we did was we first looked at the hardware architectural metrics. Since our software is very close to the hardware, it's a BSP software, to meet the random hardware metrics, SPFM, LFM, etc. We work closely with the hardware team to figure out what are the software assumptions of use they had. So these are typically, fall into this category of periodic register reads or read after write for a register, self-test libraries that we have to write, and some sophisticated techniques like program flow monitoring. These are required to ensure that we can meet the hardware metrics. So we first looked at that, and then we derived the first set of requirements. These came directly from our system or hardware team. They had AOUs or assumptions of use, and we mapped them directly to our software safety requirements. And the next one, as I talked a little bit earlier, is based on ASIL decomposition. So even though most of our requirements are ASIL B or ASIL D, we went and looked at each of the requirement, worked with the individual software teams, and checked if there is a way to do ASIL decomposition so that we don't have to necessarily develop a higher ASIL B software. So this led to a decomposed requirements to be able to develop components at a lower ASIL. So this is the second thing. And what this typically entailed is adding safety mechanisms. This is one of the challenging parts we had. So we had safety mechanisms added at very interesting points. For example, when we have two processes talking to each other, we had something called a remote procedure call mechanism. We would do a SEooC of all the parameters in a remote procedure call and then check it on the other side. Similarly, when we have PCI or Ethernet communication with the other cores, so we have multiple cores, then we would apply black channel safing on top of that. There's multiple other examples, like every image we load has an image integrity check where we add a SEooC or a hash to the image and check it. And all of the checks has to be done at a certain higher ASIL level, typically ASIL B, whereas the actual communication mechanism or the verification mechanism itself can remain at a lower ASIL. So this helped us derive the next set of requirements. And then last, we also had what we call as a safety software best practices matrix. So every component will tell what is the list of best practices they have to follow. We had a list of around 12 best practices, and they will pick and choose, which best practices are to follow. So these are typically like stack overflow detection, program flow monitoring, watchdog monitoring, logical sequence monitoring, etc., and fault and error handling. So with these, we have derived a complete set of software safety requirements. And the biggest challenge is getting all of these various components to work with each other, and the safety mechanisms we have to add on top. One of the main challenges, any of the safety mechanism doesn't come for free, and our customers typically push back because it has overhead. Any kind of SEooC addition is reasonably expensive, and they push back and check, can we do it without SEooC? And finally, we come to a balance saying, okay, we will not do a SEooC of every single byte, but we will do at a certain bytes, but still have enough confidence that we would detect any faults. So this is the first step. We derive the software safety requirements. And once the requirements are there, we go into architecture and design. As I talked briefly, we have software running on multiple operating systems in different processes. So we had a two-pronged strategy on how to approach this. For some of the CPUs which are not Qualcomm proprietary CPUs, but more of the industry CPUs like our ARM CPU, and we had an ARC-based processor, etc. We got third-party operating systems and pre-integrated them, QNX, SafeOrtos, etc. And in some cases, it was straightforward because they already had the operating system working on the same or similar kind of CPU. But in some cases, they have to customize their operating system to our processor, in which case we gave new requirements, and then we have to work hand in hand with them and look at a lot of details on how they release their software. We look at their requirements, we look at their static analysis, code coverage metrics, we look at their design plan and ensure that we can use their software, we can qualify their software to be used in our systems. And in some cases, we had hardware and CPUs. It's primarily the Hexagon processor. You can search for it. It's a publicly available detail. And for that, Qualcomm has to develop its own operating system, which we already had. And then we couldn't find any third-party operating system which would work on them. So we took the effort to make that operating system and some other operating system similar ASIL component. So this was the first step we have to do for one of the challenges we had with this complex SoC. And the second challenge is we had the same software which has been used not only in automotive but outside automotive, but also within automotive. We have to use it in various products. We have a whole suite of infotainment products, or we call them IVA products, in which sometimes there's no functional safety at all. In some cases, there's very minimal functional safety. And we have to use the same software in ADAS, where everything is ASIL compliant. And the moment we make it safe, there's always a challenge somewhere or other, typically in performance, power, thermal, etc. So, and we can't afford to have a different software for every single use case or a different product. So we had a scalable software solution. I had a slide at the end of the deck. I will leave it to you later to go through what the basic design pattern that we use there. I won't spend time on that today. But we had a scalable safety software architecture so that the software component can be easily tuned, typically with the configuration parameters that we can use it as for safety or without safety. And you can sometimes even switch between, now I am not using this component, let's say GPU for safety, and then we allow certain mechanisms. And sometimes we say, okay, now it is used for safety, you can't allow certain things. And we add some safety mechanisms only when it's used for safety. So a few examples of that is the hardware features, especially related to power. For ADAS systems, we prioritize safety over power, thermal mitigation, etc. So certain features like dynamic clock and voltage scaling, thermal mitigation, when the temperature goes high, you reduce the clocks, low power modes, etc. were disabled for when a certain component is used for functional safety. But when the same component is not used, we will allow all these features. And the next set of architectural challenge comes from freedom from interference, or you might have had as a criteria for coexistence. And we had challenges with both spatial and temporal freedom from interference. We had a whole set of mixed criticality modules within all these various operating systems and various processors. And not only that, the various processors themselves. So we had a hexagon processor, application processor, a safety manager processor. All of them in this whole ecosystem needs to also have freedom from interference. We don't want to have a QM hardware given priority over ASIL hardware, especially when it's running safety critical use case. So we solved this with a set of memory management units for spatial FFA. We had a MMU for each of these processors, and then we also had a system level MMU called SMMU to be able to provide spatial FFI across these processors. And we also used a whole set of scheduling mechanisms Some of these scheduling mechanisms were inbuilt into the operating system. They were priority based, or they had something called adaptive partition scheduling, etc. And some of them, we wrote our own scheduler so that whenever we go into an accelerator, we control what goes into the accelerator, for example, our neural signal processor at a certain priority so that we can achieve tempo and everything. So this whole architecture can in fact be a complete presentation. I can spend an hour on this, but with the time constraints we have, I just put in the few key points. I would be very happy later to talk to any of you, either in this meeting or later, to go into some of these challenges. Especially, one of the interesting challenges is safety and security coexistence. Now we have new standard for our existing standard has given more importance for cybersecurity. You're all probably aware of the 24134. And so safety and security coexisting has become very interesting now. Which is more important, safety or security? And there are certain hardware and software designed for security. How do we make those ASIL-B compliant? So there are some challenges. I can talk to any of you who are interested offline. But this is a quick summary of in the part 6 clause 7, the software architecture and design challenges. Okay, so once we got into the architecture and design and went towards implementation, one of the challenges is pre-integration of third-party software components. As I mentioned, we had third-party operating systems and other third-party software we got. So these basically fell into 3 categories. One is we had third-party SEooC software modules. These are operating systems like QNX, for example. They have their software module as a SEooC. They have the safety manual and assumptions of use. And typically, they don't change their software to fit our needs. They just come kind of out of the box. Even though we did have a lot of detailed discussions and had to make minor changes to them, predominantly, we have to satisfy their requirements by accommodating all of their assumptions of use. So this is one set of software we had. This needed a detailed analysis of their safety manual, AOUs, and some of their AOUs we have to pass it on to our customers so that only they would be able to satisfy. And then there are other third-party SEooC software modules, which they were more willing to customize for us. So we had a processor called the ARC processor for which there were no good safe operating systems. So we selected one, but they didn't really have something for this processor, but they worked closely with us. And then they had a customized solution, which kind of meant we have to work closely with them on their development life cycle. And we have to do a software qualification of their software. So this is like the second category. And then there's a third category, which are typically open source. These are compiler C libraries, certain other libraries, which are QM components, and generally they don't work with you. It's just available open source, but you can use them. So we then took a certain version of them. We sometimes had to buy test suites from other companies to test them, and did what we call as a software qualification, which is part 8 cluster. So these are the 3 methods we used when we got third-party software components. Based on what they are used for, how long they are used for, whether it's a SEooC or not, we have to follow different strategies to integrate this third-party software. Okay, so once we had the architecture design and all the list of components defined, the next thing is onto implementation. But before implementation, we wanted to look at the tool we wanted to use to meet the implementation details that the standard requires. So this primarily we use 3 things: MISRA C compliance for static analysis, code complexity, because ISO 26262 has a clause which says the complexity of the software should be less, and then code coverage. I will quickly talk about the goals in a couple of slides. But when we are looking for a tool that we would use, we had few criteria. One is, as I said, we had a complex SOC. So the tool has to support multiple compilers, multiple operating systems, multiple processors. Typically for the static analysis, we found a lot of tools scale well, but when it comes to code coverage, where the instrumented code has to run on a certain processor. A lot of tools don't scale. So we're looking for a tool which would satisfy all these various environments we have. And then we wanted to make sure that the tool is certified for ASIL D software development. On top of that, though a lot of tools were able to find the issues in the code, etc., when we wanted to provide a violation, or we say we are not going to be able to fix this issue, we wanted a certain suppression to happen to that. So in Qualcomm, anything we cannot meet, there is a safety board which will review all the violation and it has to approve. And we wanted the tool to integrate with the review mechanism here and to produce statistics which tell there are, for example, 20 MISRA rules which are suppressed, and then you click on a link and it tells which rules we suppressed, why did we suppress, etc. And we also wanted to support desktop and server configurations. The desktop is for individual developers to work with the tools. And then for every release build, we automatically run all the static analysis and code coverage in the background and be able to produce a report in a server. So we wanted to support them. And also the tool has to integrate with the Qualcomm's continuous integration environment. And it will basically block any code being checked in if it cannot meet certain criteria. For example, if we have new code which doesn't have, which has MISRA violations which are not suppressed, then the code won't be allowed to check in. So this tool has to work with the Qualcomm CA environment so that we can gate certain check-ins. And also, ideally, we wanted a single tool for both static analysis and code. And for code coverage, it's very similar requirement, as I mentioned, but with the additional challenge that code coverage is the tool has to actually work on the actual software. Static analysis is offline. So we had environments where there are no file systems. And for example, our trust zone and certain other hardware has no file system. And then we have to use Trace32, a lot of Trace32 support for that. And for some of the processes, we can't instrument the code and put the software in because with instrumentation, we have code bloat and the hardware couldn't take that code bloat. So we have to run it on simulators and the tool has to be able to support. And also one challenge is we have very Qualcomm specific hardware and software, and we wanted our tool vendor to work closely with it and enhance their tool to make customized solutions. So we had, for example, our hexagon processor. It is not something for which we had any tool that is widely available. So we wanted our tool vendor to be able to work closely with us to develop customized solutions for them. So with all these criteria, we chose Parasolt as the preferred tool for both static analysis and code coverage. And as Dave mentioned initially, it has been a good cooperation so far. Not only were the tools able to adapt to what we had, but they provided custom solutions for us to work. With that, I will hand over to Dave for a quick introduction to Parasolt. Dave?
Thank you, Guru. I'll just remind the audience, if you've got questions, you can certainly put them into the Q&A so we can see them when we get to that point. Thank you for a moment to talk about Parasolt and safety critical industries. For more than 30 years, we've been addressing safety critical in multiple industries. But today we're talking about automotive. And for that, we have a TÜV certified solution for 26262, Part 6, up to ASIL D. This provides static analysis, unit testing, code coverage, and reporting that are required for the same. We're a member of the MISRA committee, which means we're maniacally focused on keeping up to date with the standards as far as static analysis is concerned. This would be for MISRA C, for AutoZAR C++14, for security standards like CERT C and CERT C++, as well as many others. We've got over 4,000 rules in the tool. One of the things that's changing in the environment is how teams are adopting their approach to safety critical testing with a modern development approach. And that means, as Guru pointed out, they wanted to block check-ins when they had certain MISRA violations that popped up. That means that you have to do a lot of things well. You have to have a lightweight tool chain that can integrate into the CI/CD, that supports virtualization, and most importantly, can integrate the testing in a workflow that supports the feature branch development. We do all that and more. And then really specific to the talk today, we are uniquely positioned to assist Qualcomm clients with the only 2 certified solution for the Hexagon tool chain. So if you will be adopting some of the Qualcomm technologies that Guru is talking about today and have safety security requirements that you need to be testing, you will probably want to talk to me. It's a pretty exciting piece of news that we're sharing here today. With that, I'll hand it back to you, Guru.
Thanks, Dave. Okay. So now going a little bit into detail into what kind of goals we set. We had this pretty stringent goals for static analysis and code coverage. So all our modules which are ASIL compliant, ASIL B or ASIL D, we didn't have any ASIL A or C. We had only ASIL B and ASIL D, B as in Bravo, D as in Delta. All the MISRA mandatory and required rules shall be fixed. Having said that, we did allow tailoring. A team can tailor that they won't follow certain rules, and that would be reviewed by a board and approved. And also we allowed case-by-case separations. For certain software like operating systems, it was very challenging to fix certain rules because the MISRA rules were very too stringent for something at a really low level software that we have. So we did allow certain tailoring, but outside that, all the MISRA mandatory and required rules have to be fixed. And the code complexity has to be less than 20. In fact, it has to be less than 15. And for 15 to 20, we allow with approval from a board for all the functions that we have for ASIL-B and ASIL-B. And similarly, we mandated code coverage of 100%. Again, there's a caveat to all of this. Most of the modules got 100%, but something like operating system, they were at 95, 96. And then we reviewed every line of code which is not approved. And the Parasolt tool does a very good job telling which line is covered, which line is not covered. And they have to get an exception from the safety board on why this can't be covered and why it's okay for them to be not covered, and we will not still violate any safety rules. So, as I said, any exception is reviewed by a safety review board, and we can suppress it in the Parasolt tool. And when the tool generates a report, it will tell there are this many violations open, but there's also this many which are not fixed, but suppressed. And a check-in was blocked, as it told, if a certain static analysis criteria was not met. And when we went to the safety software assessment, we showed them the Parasolt reports for any component they want and provided detailed static analysis and code coverage. So this is just a quick capture on the achievements. So we were able to meet all these goals. We were able to get code coverage for all this complex software, some without a file system, and we need a very custom solution from Parasolt. But we were able to meet code coverage for all this various hardware and software, and show the proof of that to our safety assessor to get through the assessment. Okay, now after the implementation, so the implementation is primarily having those coding guidelines and the code reviews, but heavily we leveraged on Parasolt tool to be able to get us the required static analysis metrics and the code coverage for our unit testing. And the next one is fault injection testing, for all the right side of the V, the unit testing, integration testing, and testing of the verification of software safety requirements. There's nothing very special in safety except for one of the key differences, the fault injection testing. So we have to spend quite a bit of time with fault injection testing. Again, it's very complex for us because it's not like we have a single ECU into which you can generate faults easily. You have all these sub-processors and accelerators into which we have to generate faults. So this basically, we use the software safety requirements as well as our safety analysis, FMEA, FDA, DFA, and as well as the FMEA from our hardware team to decide what are all the various faults and how we would test. And we executed the fault injection testing during various stages: unit testing, integration testing, and software testing. And we had the test coverage to ensure all the requirements are covered and all the faults are For the approaches for fault injection testing, as I said, it's a bit challenging. So we use this whole set of various ideas we had or approaches for fault injection testing. One is sometimes the first one, we modified our software to have special APIs to be able to generate faults. For example, we send wrong input parameters, or we're able to call a sequence in a wrong way, etc. And some of them, we had a fault injection module which will corrupt the incoming data. So we have something which can corrupt camera frames, corrupt the PCIe packets, etc., and then see how our hardware and software dealt with. And the next one, we had like a special module which we would use only for fault injection testing. We replaced the actual software module by a DUT code which is modified. So we corrupt internal variables and we corrupt the flow. And whenever you call an API, it will give a wrong result. And then we would say how we would handle those faults. Also, we have to use quite a bit of debugger-assisted fault injection. So this is basically, we would set breakpoints in various places. In some cases, unfortunately, this is the only way. And then when it hits a point, we will go and change a variable or change a register value and then continue the flow and then see if the fault would be generated, and we would be able to handle those faults. And also we used, in the last point, we used trace32 extensively. So we would go and connect directly to the hardware and change certain register values, or write to a register, for example, to generate a ECC corruption, etc., and then do our testing. So we had a combination of all these approaches. And as I said, with the complex SOC, we have these various inputs coming in, outputs going out, and internally they talk to each other, and we want to introduce faults everywhere and then be able to ensure that the fault is handled properly as expected. One of the interesting things with fault injection, previously, when we did our software testing, we mostly kept the testing to within Qualcomm and say, hey, these are our test plan, test results. Any customer can just, come and ask for any test plan to be executed. We'll execute for them to ensure it all works. But with fault injection testing, our customers showed a deep interest in being able to reproduce it themselves, which was kind of a very good, very interesting revelation for us. So we typically don't expose a lot of these details to our customers on what kind of registers we have due to proprietary reasons, and how you can corrupt them or give them code which is on purpose as a fault. But when we got into functional safety, we realized that our customers have to be able to trigger the same fault so that it is handled at their level at a higher application of MCU. And since safety is so critical, they will basically take all our fault injection testing, reproduce it in their environment, and make sure they also handle that. So we have to not only give detailed documentation on our fault injection testing, but also provide them all the scripts which are required, the trace32 access, everything, so that they pretty much have the same environment as us to be able to do the fault injection testing. Okay, I think we're almost running out of time. So we had an external assessment with a company called Myra, and we were assessed for ASIL-B compliance, and some of the Parasolt tool features were very useful, especially to be able to show the suppressed issues and to, in a single place, be able to show all the static analysis and code coverage results. Okay, this is the last slide. So the key takeaways are, for safety software compliance of a complex SOC software, don't jump into implementation or coding right away, but spend a lot of time on the architecture that we need to have. Sometimes I hear, there's an impression like safety is about doing what you do, but test it well, fix all the code issues. But architecture plays a very key part when we want to achieve compliance for SOC software. So this primarily, as I talked, adding all the required safety mechanisms, having a safety case to say whatever you're doing is ASIL-B compliant is very important. Then tool selection plays a very key role. We have the right tool that goes a long way, not only in being able to meet all our goals, but to be able to show to the assessor that, we did meet all the goals. Documentation and proof that we did is very important. A project-specific tailoring is also a key, because SOC has multiple components which come from everywhere, from within your company, from third-party companies, some QM, some ASIL, some SEooC, and it's very important to have project-specific tailoring. You can't apply the same scale to all the various software components. And on a similar line, strategy for achieving ASIL compliance of pre-existing software has to be defined because it's just practically impossible to rewrite every piece of software you have or write a software from scratch just for ISO 26262 compliance. You have to be able to use pre-existing software, but use it in a smart way so that you can achieve and prove ASIL compliance. And careful selection and integration of third-party software is required. Most of the software you have is available somewhere, but would it be ASIL compliant? Would you be able to prove and integrate it well within your ASIL-B system is the key then. So we have to have very careful selection and integration of third-party software. And the successful assessment, we had a set of assessment meetings almost over 6 months to be able to achieve our assessment. And one thing we realized is it's extremely important to have not only strong evidence, which we had, but strong argumentation. So we have to spend quite a bit of time to provide argumentation in our safety case on why what we are doing makes for a strong safety case. So that is something we have to focus, for a complex association, we have to focus on quite a bit because all these various interactions with it. Okay, so this is all I had, and thanks a lot for your time. If you have any questions, I would be happy to answer.
That's brilliant. Thank you, Guru, for a great presentation there, and thank you, Dave, for your input as well, of course. We do have time for a quick few questions. I've got one here, so lined up and ready for you, Guru. Someone's asked basically, how long did it actually take to get through the external assessment? Do you have any advice you can share on optimizing that process?
Yeah, definitely. So for us, the external assessment took from beginning to end around 6 months, but I would say we had a 2-month stretch, which is kind of the final stretch where, where the assessor initially gave a certain feedback. We have to go and work on that and then again go back to them for a further assessment. So it's a very, very, very good question. And the reason we were, even though 2 months or 6 months looks like a long time, it is kind of relatively small, I would say, since the project goes for a few years. So what we did, even before the external assessment, we had a different consultant due to independence requirements who would basically give us a friendly assessment. So basically, once we did the requirement, we went to our consultant and he would tell us you would pause the assessment only if you did this and this changes. And so this is kind of an assessment, but it's, it's like a friendly assessment, though they will give us all the feedbacks. They call them findings. So all the findings, and some are, they call it non-compliant, some are advisory, etc. And then we'd go and fix and again go back to them. We didn't do it for every single module, but we did this for a selective set of modules. And then once we learned that, we applied it to all the modules. Similarly, after our architecture and design phase, we did the same. After our static analysis and code coverage, we did the same. And once the friendly, assessor basically gave us an approval that it's all good, we then went to a different assessor for the formal assessment. Even with that, one challenge is every assessor has his own way of thinking, or he might pick a different software module to assess. So it's not like one assessor says good and another still might have issues. So we went to a second assessor and he still had quite a few things that we had to provide more evidence and argumentation. So I would really recommend engaging with a safety consultant. If, as far as this is the first time we are doing it, especially if it's the first time, who would give you feedback and you can fix before you go for another assessor who would do the formal assessment.
Okay, so it's like getting that kind of two-step authentication, I suppose, realistically. No, that's a really interesting point, and I hope that addresses your question there as well. There's actually sort of, I suppose, almost a second part to that as well. Someone's asked, for the Parasolt tools, why is TUV certification important? They've asked, what if I use sort of open source for testing?
Dave,
excellent. Oh, this is Dave. Maybe I should take it.
Yeah, by all means.
Yeah. So it's a great question. And we, Parasolt, get asked this quite frequently, as you can imagine. The major value, quite simply, is time. The second value is capability and the risk that you can't actually perform the testing that's required. As Guru just pointed out, one of the things that was really important for the assessor is having strong evidence. And being able to collect that evidence means you have the capability to perform the types of testing and get that data in a useful format that the assessor can see, navigate, understand. For ASOL D, for example, you have to do MCDC coverage, and you have to be able to collect that code coverage on target. These are really complex things to do for an embedded system. Back to the first part, if you don't use a certified tool and you use open source, you have to qualify that tool. And it can be costly as far as time and effort is concerned. And for open source, once you've done that qualification, you kind of have to lock that tool down, because now you cannot introduce new software changes once you've done that certification. So it kind of limits the value of open source overall for a safety certified project. And then lastly, Parasolt, because we are TÜV certified, we have designed features that are meeting the needs of customers like Qualcomm and many other automotive customers, in particular for meeting the goals of 26262.
I think that is all the questions we've got. But for now, thank you so much, Guru and Dave. I don't know if you have any final quick words you'd like to say.
Thanks, Josh, for arranging, and thanks for everyone who attended. Thank you very much.
Thank you all for your time.
Thank you to you both, and of course, thank you to Parasolt.